Welcome back. And this time around, we are going to learn the concept of Diels-Alder reaction. Okay. Diels-Alder reaction. Okay. And for a Diels-Alder reaction to occur, you need two components. One is called a diene, and the other is called a dienophile. Okay. Okay. These are the two components that you need for a Diels-Alder reaction to happen. Okay. Very good. So let's look at an example. All right. And another requirement is the double bonds must be alternate. Okay. I'm going to write that down here. Now, textbook may not necessarily give it in this way that I've written it here, because I've concised it to a small piece of information. Okay. Alternate double bonds. If you don't have alternate double bonds, first, having two double bonds right next to each other, I've pointed out repeatedly, it's a pretty unstable situation. Whereas when you have alternate double bonds, that changes the picture. It's a more stable form. So let's say we react this molecule with, say, this molecule. Okay, that's essentially just a CH2 versus CH2, CH, CH2, right? So if you notice, this bond is alternate to it. So let's start moving, and this is where things can get a little tricky. Okay, so a double bond goes into an empty spot where there is not a double bond. Okay, and this double bond connects to this carbon, okay, as a bond, like you will see when I finish drawing this molecule in blues and pinks when I'm finished with the product, that this again acts like a messenger. You can ask me, why did I not give a positive or negative in the successive steps? Is because nothing is lost, nothing is gained. This is just merely rotation of bonds. So in that case, this should have got a positive, but then what is lost here is gained here, and then the sequence continues. And this double bond gets attached to this carbon. Okay. So what does it all mean? Let's go ahead and complete the product. I'm going to write alternative. This part I'm going to actually write it in blue so I can highlight the pinks. Okay. What you started with stays. You cannot change the structure. So I'm just going to leave this way here. Okay. Now what has happened here is the pink bond, okay, the bond has moved from here to here. So you write the bond here, right? And this bond here is used as a bridge to connect this carbon and this carbon. Okay. Of course, I'm not drawing a perfect cyclohexane. I can redraw it once I finish drawing. But you can do the same. You can just draw like a rough sketch of it and then go draw a perfect version. And this bond has connected this carbon and this carbon. Okay, you're connecting carbons with a bond. So this is what that molecule would look like when you're finished. So I'm going to rewrite this. This means AKA. I'm just going to draw this all in one color so that I can, okay, this is just a cyclohexene. Okay, now in this case, this is your diene, means it's got two double bonds, and this is your dienophile. Okay, and if you notice, it is alternate double bonds, right? Double, single, double, right? There was single here. I mean, it's imaginary, but you can treat it as empty space. Double, single, right? That's why we are able to rotate bonds. Now, if you Diels-Alder reaction will not happen if you cannot complete that sequence. Okay, I'm going to show you an example down the road. Right? Now, there is two important things to remember. Okay, one of them is, let's say I react, okay, this diene, okay, plus a dienophile where the two groups are adjacent to each other. Okay, I'm just going to call it some random R and R prime. Okay, R and R prime, it could be anything. Okay, these are two identical groups, or we can even keep it as R and R. Okay, these two groups are adjacent to each other, so they are cis to each other. So this must be trans, right? I mean, these two are cis to each other, these two are cis to each other, right? So let's start moving our bonds. Okay. Okay. This comes here, this comes here, right? So when you're finished with the molecule, okay, I'm just going to draw a cyclohexane because that's essentially what we have made. Okay. These two groups are cis to each other. Now don't confuse this with diequatorial or diaxial that we learned for our cyclohexane. Okay. These two groups are cis to each other. Okay. So we indicated by two closed arrows. Okay. And so that is if these two groups are adjacent to each other. Now, what if those two groups were not adjacent to each other, but were actually opposite to each other? Okay. So that means this would come here, this would connect to this carbon here, this would connect here, right? So since the two R groups are trans to each other, we indicated by one closed and one open wedge. Doesn't matter which one you give open, which one's closed, it's entirely up to you. This is a cis product. This is a trans product. Now, it's very important. Your dienophile can have cis or trans conformations, but your dienophile can have both cis or trans, but your diene must always have cis. What I'm referring to is okay. You know, we looked at this is our diene, right? You have no problems with that. This is our diene, right? And we looked at two different scenarios where the R's are on the same side, right? Or we also looked at, so this is reacting with this, or we also looked at this, right? So this gave a cis product, this gave a trans product. But in both those cases, okay, the dienophiles can be a cis or trans, but the diene is always cis. Okay, diene is always cis. Okay, what is not possible is this. Even if this were to be cis, okay, this is not possible. No reaction. Okay, because the diene is trans here. The two double bonds are trans to each other. This and this are opposite to each other. And this is not possible. The diene is always cis. The dienophile can be cis or trans. If the dienophile is cis, then you get a cis product. If the dienophile is a trans, then you get a trans product. Okay, this is called conformers. People say these are isomers. They're not. They're conformers because cis and trans are not isomers. They are conformational isomers. I guess you can call it conformers. Okay, these are conformers, not isomers. Okay. Okay, because cis and trans have a totally different meaning than you have isomers. So these are conformationally different. That's what, if you remember, even when I write questions, determine the R/S configuration, right? Configurations. So conformation, not conformers, not isomers. So your diene is always have to be cis. Your dienophile can be cis or trans, and depending on whether the dienophile is cis, then you get a cis product. If your dienophile is trans, then you get a trans product. Okay, Diels-Alder reaction is very important, which is why we are learning it. And I've tried to keep it very simple within this one video, and maybe in the next video I'll try to work out maybe a couple of different examples just to see how the bond moving can be made easy. All right, so stay tuned.